Okay, today we're going to talk about smart contracts and distributed apps. So we covered Bitcoin. We won't be doing much with Bitcoin in this class, but it was a distributed ledger of financial transactions, and it's mostly being used for currency transfers. So it's not really changing very much, and the abstraction that it provides is pretty simple. So what it does is it gives you this secure, immutable, global ordering of transactions. So one of the Bitcoin developers came up with this idea of, hey, what if the transaction, instead of a financial exchange, were the execution of a CPU instruction? So what if you treated the blockchain as an execution record for a computer that includes all of the programs on that computer and their execution states, like the process state, if they were executed. And that was his goal. His goal was to extend this blockchain to create a replicated distributed state machine that is able to store arbitrary data, not just unspent transaction output, which is what Bitcoin stores, arbitrary data. Store persistent programs, so things that can be executed, and their execution states. Support interaction with this code, so function calls from any of us on the block in the public. So users can call into them and have results. Whenever I call into a smart contract, the results of that execution should be visible to everybody. So that's the idea of smart contracts, and it's a misnomer. So in computer science, we usually don't judge things like this, like what's smart and what's dumb. There's a lot of dumb smart contracts. So these, the more technical term, or I guess the more precise term in terms of what we would like to name it, is something like persistent scripts or stored procedures. So if you take the database class, a stored procedure is code that executes on the data backend, so that you don't have to bring the data back up into your node, process it, and then restore it. It just is stored over there. And that's the execution model that you kind of have with the smart contract on a blockchain. You issue a function call, the data is stored with the contract, and then it does something on the back end. So persistent scripts or stored procedures are what you can think of, because smart contract doesn't really mean anything to a computer scientist. Well, at least not to me, not to this computer scientist. Some definitions. A computer program executed in a secure environment that directly controls digital assets. So that's one way you can think of it. Another way is a computer program that digitally facilitates, verifies, and enforces the performance of a contract, its transactions, in a trackable and irreversible manner without a third party, a trusted third party. So the model of a smart contract is that you first commit a program to the blockchain and all of its instructions and its initial state. You have to have an initial state. And then you receive inputs and produce outputs via calls into that contract and update the blockchain thusly. So yeah, the state changes that are being the state changes that are being emitted from program execution are duplicated and replicated and stored persistently in the blockchain. Okay, so it's got this shared state machine paradigm. You begin with a contract, its code, and a genesis state. And this is similar to the Coinbase. You have to have some starting point of a smart contract, and this is typically when you create the contract on the blockchain. And then there's a constructor that you call that says, this is the initial state of my process. It's sort of like program loading in a computer, where you're loading the program, you get all the sort of the state that you want set up, and then you call main for a C program at least. And then the distributed consensus is implementing a shared state machine that will transition the contract state from one state to another, and the blockchain is going to execute these transactions and take it from a genesis state to another state, and then more transactions to another state, and this state machine could explode into any number of different states, including the state where all your money is lost. That's an important state that we want to avoid, typically, unless it's intentional. Unless you're the contract owner and you want to steal everyone's money, that's the own everybody state. So single shared machine, single shared persistent memory storing the code and any of the variable values that you have. So if you're using a variable and to keep track of like your balances, that's stored in that can be stored on the blockchain in across all the nodes. So you can think of this as a persistent process. It's basically the abstraction of a single global computer with shared state, which for me reminds me of the mainframe computing model. When I was an undergraduate, that was my computer. Like we had one shared computer across like the entire engineering school. It was this IBM mainframe, and everybody ran all their stuff on there, and then everyone could see, you know, that's where the engineering computing state was. So yeah, this is proof that everything old is new again. Everybody now is going back to this mainframe model, which is what the block, like storing a computer or implementing a computer via a blockchain. That's basically what this is. And so you get the, like when I was programming my initial programs, they were really dumb programs. So this is really nostalgic because then I can actually look at really dumb programs again and think that, hey, this is like 30 years ago. But oh well. This is a picture of what's going on. So you have a smart contract that multiple parties interact with. There are some transactions that go through this smart contract that change the smart contract state. This is included in a block, those changes, and then that's committed to the ledger in a consistent and persistent manner. Okay. So this is used to implement distributed applications, which are called dApps or dApps. I actually don't know how you say that. I'll call them dApps. But one of the things about this model is that the stuff is immutable. The contract code that you publish and you create the genesis state for, that's there forever, right? Like you shouldn't be able to erase that. That's the whole point. But because it's there to stay permanently and can never be modified or updated again once deployed, you have really no mechanism to patch that code. So this is the complete opposite of CI/CD, so continuous improvement, continuous deployment. If you're taking, so I'm teaching the cloud class. If you're taking the cloud class, it's all like, yeah, let's just update. Oh, it broke. Let's just update that next week or tomorrow, and then we'll push it out again. Well, this is the opposite. Like you totally need to do waterfall on this thing because you have one shot at it. Like you have one shot to get the thing right, and if you don't get it right, well, then there goes someone's money. Hopefully not your own. So this motivates security. So this is a quote from Konstantinopoulos, who has written many books on Bitcoin and Ethereum, or the best books on Bitcoin and Ethereum. So you really need this to be secure, which is why the whole second half of this course is about security issues on smart contracts. Okay, so you have to make sure your contract has no vulnerabilities before you deploy the thing. And this is why you have to do things like code auditing. Like you have to actually get your testing and your validation done ahead of time. And this is why program analysis and symbolic execution matter. At the very end of the course, you're going to be able to point some automated tools to try and exploit smart contracts that have been developed and deployed. Okay, so if you do have a fix, so people are getting wise to this. So fixes require a completely new contract to be deployed and all of the users moved over to the new contract address, if possible. So people are trying to write this in to their current smart contracts. It's like, can I have a kill switch on this contract that just moves everybody over from one address, contract address to another, including transferring all of maybe the financial state. So this is what they're looking to do, is build these things in there. But the problem with this is that this really protects the contract owner, but not the users. Like, how do you know if that kill switch isn't going to be used to steal all your money? The whole point of a smart contract was to have code as being law, so I understand what I'm buying into, and then nobody can sort of like take it out from underneath me. But if somebody puts a nefarious backdoor in the smart contract and I put all my ether in there, and then they trigger it to take all my ether away, I have no recourse, right? So this is where, this is a gray area. So before you send your ether, you might actually want to analyze the smart contract yourself. Like, what can the deployer of that contract do in terms of manipulating the contract? Can that person transfer all the money to him or herself? Is one of the things you might want to think about. Okay, so some general uses for smart contracts. Automate or streamline the operation of a trusted third party, where trust is typically expensive. So if you have to bootstrap your trust with a person, for example, like a notary, and that notary is the human that you're having to pay to do certain things, well, if you could have that notary be able to streamline his or her operation, you might be able to make things cheaper. Automate transaction processing, where the processing is done manually, person to person. Implement legal contracts with unambiguous terms that can be expressed in code. Not all contracts can be expressed as a program, but those that can be implemented on a blockchain with a smart contract. Create scarcity in a digital domain, so things like currencies, things like collectibles, things like deeds, or certificates, for example. Here's one. So I'm going to go through some of these. Sports betting. Like, you could do sports bets on a blockchain. So, for example, you could have this contract that says if Tiger Woods wins the Masters in 2019, transfer 14 times your bet amount to a particular party. And that was Tiger Woods' odds at the time that he won. I looked up, NBA basketball just started. So the odds that the Trailblazers win a championship this year are 3,300 to 1. It was actually 75 to 1 when they had made the playoffs last year, so I had to update this. I looked it up. So you could, if you were doing this sports betting dime and you were taking bets on a blockchain, you could totally take those bets in and then implement this smart contract and then have this predicate triggered by maybe some NBA signing key that certifies the results that, yes, the Trailblazers won the championship. And then you could do all your payment immediately on a smart contract, which may or may not be nice. I don't know. It depends on if you like betting. You could do a digital will on a contract. So this is a dead man switch. So you can execute code in a will to transfer any kind of digital assets upon the owner dying. And then the idea would be maybe the coroner's office has a private key that could be used to sign a transaction that triggers the execution of your digital will on the blockchain. One that you'll implement is a trust fund, or you'll be toying with as a trust fund. So a trust fund is you give your kid money after the kid gets 18 or something like that. So then you have your year, and you can check the year on the blockchain, and then all of a sudden, if it's greater than 2040, you transfer the balance of the fund to your child's wallet. So maybe this will be the generation where everyone's got a digital wallet instead of a Facebook or Instagram profile. Okay, another thing you could implement are option contracts. So option contracts are done as typically incentives for employees and executives. So at a particular date, if you've been at the company for a certain time, you are allowed to buy stock at a discount, and that's your option price. And these things can be triggered by either a condition for the stock price or the date in terms of your vesting. And then you can execute these things according to the coded terms. Those conditions are very precise in an option contract, so they're very natural to express in code. And you could potentially have these things being done with parties that are unknown to each other, except for their public wallet address. So you don't even need to meet face to face before you can do these things. One of the things that this would do if it was actually put on a blockchain is that it affords regulators greater transparency. to see any shenanigans going on with compensation. And so you would be able to, if these contracts are made and put on the blockchain, then you would be able to inspect these things for any anomalies or abuse. So that's one of the things that people have thought about. Another kind of contract is an escrow contract, and this is, again, an expensive trusted third-party operation. You will be building one of these in one of your labs later on. So trustworthy asset exchange, where you have two parties, A and B, who don't necessarily trust each other. Like, I want to buy a house. It's like, I can't exchange the money for the deed, like, simultaneously. It's not how it works. So you have an escrow company, and the idea of an escrow company, if A wants to transfer something, or if A and B want to transfer something to each other, A wants to buy a house, for example, from B. So A will send money to E, which is the escrow agent, and in this case, it's the escrow contract. And then typically what would happen is that B would then transfer the digital deed or the item to A, and then E would hold this money. And as soon as this has happened and the escrow agent can verify that this has happened, then what E will do is transfer the money over to B. Now, typically, an escrow company takes a cut. I forget. Does anyone know what the cut is for real estate? I'm going to do real estate here. There's like some cut, like maybe 0.5% or 1%, and that's a lot of money, right? For basically just holding the money for a day. That seems pretty lucrative as an escrow person. So the function that the escrow company is actually providing is protection against this. So A transfers the money to E, the money to E, and then B says, I won't give you that deed. And then after a certain period of time, E returns the money back to A. So this is something you could do very naturally on a smart contract, which is what we'll do. Okay, so this is 20 lines of code, and then you can avoid paying thousands of dollars if this is done digitally. If this can avoid paying the money, makes this less of a burdensome operation for the transfer. Another thing that a smart contract can support are multi-signature, multi-party asset transfers. So one of the things we didn't talk about with Bitcoin is that it did have this idea of a multi-signature wallet built in natively. If you wanted the same kind of functionality where you didn't want a particular piece of code to execute unless multiple people signed off on it, a majority of shareholders, for example, signed off on it, then you would have to do that inside the smart contract itself. So you would have to implement some kind of code that does that. So in this case, I have a function here that is the sale of all of my company to someone else, and then I would require, say there are 5 stakeholders, I would require 3 out of the 5 to actually invoke this function before it would actually execute. That's the idea. Initial coin offerings are super popular as smart contracts. So these are things that are bound to what we call ERC20 tokens. And these are similar to stocks. They're just a way of wrapping up value of a particular denomination and then to be able to trade those things for each other. So this is a virtual version of an initial public offering where you're selling shares for a company in exchange for cryptocurrency. So you would say, here's your digital asset, this token. You can buy it by giving me a certain amount of Ether, and then that is my currency that I can use to start my business up. So there was that podcast, the Polyswarm podcast from the first week. That's what they did. They were like, hey, we have this great idea. We want to pay people on the blockchain for malware predictions. Like, they're going to do some malware analysis. They're going to basically judge whether or not a piece of software is malware or not, and we're going to award them money, like cryptocurrency. And in order to bootstrap that whole thing, they were like, okay, we need an initial coin offering. We need to be able to start the business up, and that's what they did here. Okay, so it's also been used to bootstrap alternate cryptocurrency networks, so EOS and Tron. They had initial coin offerings on Ethereum. This is I forget which one. I think this is Tron's contract address. And then what you would do is you would go to that contract address and you would pay from your wallet into it, and then you would get Tron tokens. And these things this contract was such that this would give you entry into the Tron network with a certain amount of currency at the beginning. It's been used for virtual crowdsource funding, so like a virtual Kickstarter. So it's a similar idea where if a Kickstarter raises a certain amount of money at a certain amount of time, then it will execute it will execute the contract so that it would give the recipient that amount of ether so that they can then go off and implement whatever they proposed. If you did not get to the funding goal, then it would just return all the money to the people who contributed it. So this is another one. This fundraiser one is something that you'll implement later on in this class. Okay. It can be used to implement stable coins as well, where you have coins pegged to real dollars in terms of an exchange rate. And that's something that is similar to what DigiCash had in mind, where your blinded bill is $1. The other thing that it can implement are centralized exchanges. So like your stockbroker is a centralized exchange where you give your assets to this broker, and then the broker is managing the trading and the exchanging. So that broker holds the assets directly, and then the users will deposit, withdraw, and trade on that account, all within this central contract. So similar to E-Trade, which is one exchange. Here are some examples of this: Bitrex and Polynex. And you can buy, sell, and trade over 100 supported ERC20 tokens. That's the address of the, I forget which one of the two. But what happens if the exchange is hacked? So the history, so Mt. Gox was the first exchange. It held a whole bunch of people's Bitcoin. And then it got hacked and lost 740,000 Bitcoins and then went bankrupt soon after. So if you're holding the actual assets, well, these are the wallets worth. The wallet's worth that many Bitcoins, and you get hacked, then yes, having it be centralized is not necessarily a good idea, because now you are in charge. Mt. Gox was in charge of operationally securing everyone's private key. Because what happens is okay, here's my account. I want you to manage all my trading. Here's my private key. And then when I say to exchange, you have the assets there now to do the exchange for me. That was the function that Mt. Gox was providing. And it made it very easy for a user to use it, right? I just have one account on my broker, and I just tell them to do this, that, or the other. I don't have to worry about anything. But this is what happens when you have a centralized exchange. It is an enormous target for hackers. So this motivates decentralized exchanges. The exchange contract in this, they don't hold user assets at all, or wallets. No private keys. Anyway, I don't want any of that. What they are doing is they are being the facilitator for exchanges. They're doing the money-making operation, or the market-making. What is it? Any business student here? What is it? Market-making was where they match the buyers and the sellers together on the stock exchange. Stock market, yeah, that's what I think it's called market making, matching the sellers and the buyers, and then they would trade directly, right? Like they wouldn't have to go through me as an exchange. Oh, I'm facilitating the sort of like a peer-to-peer trading is what a decentralized exchange would do. So here are some examples of this: Ether Delta and IDEX for trading ETH and ERC20 tokens. This is a picture of it. So on the off-chain, you're going to do some kind of balances and sort of you're going to take orders and be able to match them off-chain. And then when you have something that needs to be exchanged, then the users, the maker and the taker, will interact with that contract to do the actual exchange. And I don't have to have that user's private key necessarily to get that to make. Okay, another application are tickets and certificates. So you can think of event ticketing, where maybe you buy a ticket to a concert, it's stored on the blockchain, and then maybe when you exchange it, that asset gets exchanged on a smart contract, and then when someone goes to use it at the venue, you have the private key that was that's associated with the public key that ticket got transferred to last. And then you would be able to validate and prevent double usage. So what is being done right now in terms of ticketing could be done. You could do the trading and the actual validation of the ticket all on a blockchain. You could do timestamp certificates and degrees on a blockchain. We talked about that earlier. Another thing you could do on the blockchain is with a smart contract is DNS. So right now we have this hierarchical distributed DNS lookup system, but you could actually implement this. Since you have the distribution with different nodes running the blockchain, you already have the distribution channel, so maybe all you have to do is store the entries, the DNS entries there. So you could basically do this with, so this Ethereum name service is a service that builds DNS records on a blockchain. And so you can actually, with this, you can actually see when domains are registered and who registered them, right? And this is giving you the equivalent of what this TLS certificate transparency does. So if you take the cloud class, this certificate transparency, we have trusted a bunch of certificate authorities with all of the certificates that provide us the green lock on our web browser. And so if you don't trust that certificate authority, then what you would want to have happen is every time that certificate authority signs a certificate, you would want that to be public knowledge. And that is what TLS certificate transparency is doing. It's forcing every single certificate authority to publicize any record, any certificate that it signs. This is something that a blockchain does very well, signing certificates and then publishing them. So this is the idea of the Ethereum name service. So here's the idea. In your contract stores an array, a mapping that says who owns this domain and then what is its IP address for that domain. And then you implement a register function in this contract. So you can, if the domain is open, then what you would do is you would set the owner of that domain to the sender of the so this claims the domain. This registers a domain by making you the owner of that address. And then you can, as the owner, you can set the address. So if the message sender is the owner, then I can allow that person to send me an IP address that binds the domain. And then I can have everyone else call get IP for a particular name. And then you can just return that IP address. So this is a really simple way of implementing a name to IP address lookup using a small smart contract, which is what this Ethereum name service does. So if you want so it's really a pain in the neck to copy and paste your wallet address. You'll be doing that a lot, actually, in this class. So the idea is like, hey, why don't I have Wu-chang.eth, and that's my wallet, and then you can just send me it there. That's the idea of this. In fact, I probably should do that before someone else registers that name. But like, if I wanted that name on Ethereum, I would go and register on ENS. Okay, another popular contract are collectibles. So these are smart contracts for implementing a different style of tokens. These are non-fungible tokens, meaning that you can't create multiple ones. They're unique. So yeah, the ERC, this is just a standard for implementing digital assets on Ethereum. This is what ERC, so ERC20s are one style of digital asset, and then ERC721s are a different kind of token. So this is a game, Kitties, which is probably the most popular Ethereum app ever, where you're basically collecting and breeding digital cats. And then randomness will award you some cat with really unique properties, and then those cats are worth a ton of Ethereum, a ton of Ether on Ethereum. Okay. So the smart contract and the code running the smart contract generates these unique tokens with unique properties that are then signed over to the users' wallets as owners. And then there's no centralized authority to either duplicate or steal the kitty away. The person who has deployed this CryptoKitties contract isn't able to go and take away your kitty from you. Like if you have $1 million kitty, the owner can't go there. You own that kitty with the way the smart contract is written and with the way cryptography is being done. Okay, so that is the contract address if you want to buy yourself a kitty. That's there. There are some other games. There are a lot of gaming companies trying to build stuff on the blockchain. The problem with games on the blockchain and on Ethereum is that Ethereum is way too slow for most of this stuff. And we'll get to some of the things they have to do if they want this thing to actually be a useful computer. Here are some statistics from last year on the top 10 contracts on Ethereum. So you see we talked about a lot of these different ones already. And these are the categories. So decentralized exchanges, initial coin offerings, collectible tokens. I don't think these things have changed since last year, so I didn't bother to go find the updated. But these are the ones that have the most transactions going to and from them for the month of October of last year. Okay. Here's a pie chart. So exchanges are more than half. ICOs are close to half, and then collectible tokens are the last bit of that. Okay, so now we're going to talk about Ethereum and what it does. So the history of Ethereum is proposed by Buterin in 2013. So he was one of these core Bitcoin developers, and he had the idea to build decentralized applications instead of just something that exchanges currency. This was deployed 3 years ago in 2016, and it was really the first blockchain to support smart contracts. So it stores actual state account balances versus Bitcoin's UTXOs, where you have to actually go back to the genesis, the Coinbase, to figure out whether someone owns something. Here, there's a notion, we're going to actually store balances on the blockchain, and if you really want to make sure that that balance is correct, you have the replay of all the transactions. You can actually validate that, yes, that is valid state. But this actually helps you make things a little more scalable, right? At least for a full node. You don't necessarily need to do this. I mean, every once in a while you probably should keep things valid, but you don't have to do it on every transaction. It's not built in. Okay. So why not Bitcoin? Well, Bitcoin had this very restrictive execution model, which is actually good and bad. We'll talk about the bad part of Ethereum when we talk about security. But all you're doing is transactions and financial transactions to avoid double spending. So this is going to support a certain style of operation. What Ethereum wanted to do was to build a Turing-complete runtime that could be used for computation. And as a result, if you're doing this, you require a much higher transaction rate than Bitcoin. You also require a whole bunch more storage. Like, you're going to have to store a lot more than what Bitcoin is doing. So here's the idea. Instead of transactions, you're basically storing virtual machine states. It's a tiny virtual machine, but it's still virtual machine state. And then the transactions are basically metered. Where to limit the amount of computation that a full node has to do, because you don't want the nodes implementing Ethereum, you don't want them to fall over because they don't have the resources to implement what they're being asked to. So every full node on the Ethereum blockchain processes every single transaction and stores the entire copy from the genesis of Ethereum. So it's the state of all contracts and accounts. And there are shortcuts that you can make to make the amount of state that is actually stored less. Like Ethereum has this notion of, especially if you destroy a contract, you don't destroy the entire history of that contract, but you can destroy the contract in that it won't accept any more transactions, and then you don't need to store that on a full node anymore. That thing is done. So there are ways to get your state back on Ethereum, which we're not going to get to the details of, but scalability is a huge problem in Ethereum. So this is a model of what's going on. You have both the transactions and the smart contracts that these transactions are calling into, and every node, A, B, and C, is running a full Ethereum client that stores all of this throughout time. And you can see here, well, you can barely see this, Geth, Parity, PyEth app. These are implementations of the Ethereum full node. So we will be running Geth at the very end of this class. This is a Go implementation of an Ethereum full node. Parity is, I think this is a Rust implementation of a full node. So these are full nodes that are implementing the Ethereum virtual machine faithfully, and then storing all of the transactions on the blockchain. Okay. One of the things with this is that it has to be implemented using a secure, memory-safe, and fast language, and this is why Go and Rust are being used. They're both memory-safe, and they compile down to machine code, so they're not interpreted. Like you wouldn't want to build this in Python, for example. So this is why full nodes are typically using Go or Rust. So we don't teach Go in this department, but we do teach Rust. So for all of you who are, is Rust being offered this quarter? Anyone taking it? Yeah. So accounts on Ethereum. So you have two kinds of accounts. You have a user account, which is very similar to Bitcoin. It's basically an address that is associated with a user, like the wallet address is a user address. This is also referred to as an externally owned account, meaning that the person who controls it is external to the blockchain. And these wallets can only send and receive ETH, which are funds, and then smart contract accounts, which have the exact same address format. These are stored in the blockchain. The addresses are stored in the blockchain, and it stores code that can be called and executed from other accounts. So it can do everything that a wallet can do, but it can also contain that code and data as well as keep a balance. So there are multiple modes of use of Ethereum. So the transactions can be done between wallets. So here's a source wallet, here's a destination wallet. I can do exactly what I did with Bitcoin, just transfer ETH from wallet to wallet. I can have transactions that go between a wallet and a contract. So here I have a source wallet, and I want to invoke a function in a smart contract to run and update some kind of code. So I want to buy a token. So I'm going to call the buy token function, and I'm going to send some Ether, and then this is going to run and then credit me a token for the amount of ETH that I had just purchased. And then that state that I own that one token is now inside the contract as well as my ETH. So that's the idea. You can also have contracts calling each other. So automated calls of contracts to other contracts, and this is what you'll end up doing for some of your capture the flag exercises later in this course. Okay, so wallet addresses and smart contract addresses share the same format. It's the same idea as with Bitcoin. You have some kind of private key. This is typically ECGSA, which is used to digitally sign any of the hashes of transactions that you want to send. It's 66 characters, so 66 times 4 bits per character. That's several hundred bits of key. And then you have a public key that's generated from the private key. That's basically the last 40 characters of the Keccak hash of the public key. And this is what your wallet address would look like. So in the first lab, you'll be setting up a wallet, and you'll be getting a wallet address that looks like this, and this is the wallet address I want you to commit to your Bitbucket repository. I need to know what your identity is on the blockchain, and this is what your identity will be. And you'll notice this looks case sensitive, and it's case sensitive for a reason. There's a built-in checksum that's being done here with the capital and the lowercase letters. So because people, when they're typing in addresses, you can get like an off by one error, or like it's hard to type this. This is why the Ethereum name service exists. It's hard to type all that stuff in and not make an error. So the way what they did was they implemented a checksum inline, which is using the capital and the lowercase letters. And there are some interfaces that require this checksum address versus one that's all lowercase. So I wanted to bring that up because that'll eventually get people as they're working on this stuff. Okay, so the problem with the private key is that it's subject to attack. So yeah, if someone has your private key, you can score, well, this hacker was just guessing them. So if you have an insecure, if somebody finds a flaw in how the private keys are generated in ECDSA, then they're in business. They can guess a lot of the wallet keys easily, and that's what this person is trying to do, guessing the private keys and then scoring millions. So it could be as simple as someone misconfiguring their ECDSA algorithm. Like if MetaMask, if somebody finds a flaw in the parameters of MetaMask for generating those things, then you're hosed. Well, not in this class, yes.
So this wasn't a flaw with ECDSA, it was a flaw with some particular configuration?
I think so. You'd have to go and read the details of that, but the same thing applies to RSA. RSA is also notoriously hard to configure correctly to get randomness. But that in the crypto class would be a good thing to look at for that. So smart contracts, so some of the things that smart contracts can do and they cannot do, they can hold funds. Basically, they can keep a balance, just like a wallet. They can send currency to other accounts, and these other accounts could be other smart contracts, or they could be other users external to the contract. They can have persistent storage on a blockchain that's both readable and writable. There's this notion of storage variables. When we get to actually programming a smart contract, there are storage variables, and then there are these local variables that don't get stored. So you can think of those as storing data on disk versus in your function call, just having an ephemeral variable that gets used in the register and never stored. So that's the idea, sort of to have that stored state in a contract is one of the things that Ethereum allows you to do. It can contain code and execute it. So it can have functions that can be called by wallets and functions that can be called by other contracts. What it can't have, it cannot create Ether. So only a miner can actually create the currency, so that the incentive system is such that the mining operation to keep the whole thing secure is the thing that generates currency. It cannot query an external API call. And the reason why it can't is because you have to guarantee that when everybody queries that external API, they get the same result. Because this is a global state machine that you're implementing. If you have your contract call a REST API and then someone else calls that same one and gets a different result, you're inconsistent. So there is no oracle per se. This is one of the things that Buterin is working on, though. How do you effectively implement some kind of oracle that can be used to inside the context of a smart contract? So right now it's not there. And there's no sleeping on a blockchain. So yeah, you can't solve the halting problem on a blockchain. So if someone tries to do an infinite loop, you want that to be terminated. Okay. So how does it actually work? So smart contracts are developed on a high-level language, and then they're compiled down to Ethereum virtual machine bytecode. And then this bytecode runs on the EVM. This is very similar to what you might have come across with Java, or even Python goes down to an intermediate bytecode now. .NET does the same thing. So you take that higher level language, you compile it down to bytecode, and then this stripped down EVM executes that bytecode. So the contracts are typically small, on the order of maybe 100 lines of code. Here's an example. This is the hello world. Maybe you have a contract that just prints a greeting. This is what you write. This is a Solidity program. This is not a Solidity. Is it? Yeah. And then this is what it compiles into. So this is your bytecode. And this is what gets pushed into the blockchain, right? A bunch of bytes. And if you ran a disassembler on this thing, just like in CS410, you would run a disassembler on x86. x86 looks like a blob of bytes. And then you run a disassembler. Well, this opcode is push 60, then push 40, and then mstore. So these are the individual EVM instructions that that contract implements. So this process allows you to take multiple programming languages and produce a contract. So in this case, this is like LLVM. LLVM, you can take, C, C++, Java. You can compile that down to LLVM bytecode, and then the LLVM machine will actually run the thing. One of the things in terms of language choice is that you want to make sure that the language that you're programming in to produce this EVM bytecode is what you want, that it provides you the right abstractions and the right safety properties so that you don't shoot yourself in the foot. So initially this thing was done with Serpent, which was this Python-like language that exposed a lot of the lower level implementation issues on the underlying virtual machine. But now almost everything is done in Solidity. I think it's like more than 80% of all contracts, 80 or 90% of all contracts on Ethereum are written in Solidity. And this gives you types and variants, and it basically has JavaScript as a founding sort of syntax, as a base syntax. And then you can easily just compile Solidity down to the same EVM bytecode that Serpent compiled into. But all of these, the problem with Solidity is that you can easily write insecure smart contracts in Solidity. And so this is what the second half of the course will be. You'll see all the different ways you can blow yourself up with Solidity. So this motivates Viper. And so this is the potential language to replace Solidity, and this is more Pythonic. And you'll be doing some contracts in Viper just to see the difference between the two languages. Okay, so I brought this up earlier. There are some issues with this model. The first one is the halting problem. What happens if someone tries to give the virtual machine an infinite loop, like this one? Like, can I bring down Ethereum by sending all the full nodes this infinite loop? So they thought of that. And so you can't solve this. Well, if you can solve this, you do all of us a huge favor in computing. But how can you limit this behavior? And so in order to limit this behavior, in Ethereum, there's this notion of gas. This is just like your car needs gas. You force the user to supply some gas for this computation, like currency. So in order to execute the transaction that you are putting on the full nodes, you have to say, here's the amount of gas that it's going to require. And I'm gonna supply that ahead of time. And so your wallet has to put up this Ethereum to execute that call. So the sender pays. The sender is paying for the computation on the blockchain. And if the sender guesses wrong, says, I put, 2 gas in my computation and it needed 3, then the network is going to take that gas and then not execute. Because it's like, well, you forced me to do some work, and then you didn't give me enough to do the whole thing, so I can't commit that thing to the blockchain. Well, I'm just going to take your gas because you forced me to do work, and then you're going to have to try again. And so this is an incentive model for good behavior. You need to do this because it's a shared resource. So that's the reason you do gas. So the fee is charged per computational step, and it's also charged if you want to use a storage variable. Then yes, you're going to have to pay for that. Because some poor soul, some full node running somewhere, is going to have to store all of the state that your contract is producing and putting into the blockchain. So yeah, you got to pay for it. So you limit the resource consumption to what the sender pays for. So the cost per byte stored and then per operations used. These things that are being paid for go to the miners. Because the miners are actually doing the work. The miners and the full nodes are doing all the work. They're basically renting cloud resources probably to run all this stuff, which is what your Google Cloud Coupon is about. You'll be using Google to run a node. So the transactions are specified with a gas limit and gas price. And this will be used to estimate how much the computation will cost. how many dollars, and there will be more details on the next slide, but this is your incentive. This is the way the incentives are built to keep the thing from crashing. Okay. And I should note that the motivation for this, you'll see that a lot of stuff is being done off-chain just to save resources on-chain. So this has led to a lot of innovation on off-chain things. And you saw that with the distributed exchange. A lot of that stuff was pushed off-chain so that the only thing that happens on-chain is the actual transfer. That is a result of making sure that the incentives are set up appropriately. So, example gas charges. So we saw those operations, EVM bytecode. So if I supply 111,000 units of gas, this instruction will cost me 3, this instruction will cost me 3, and it will debit the gas until either the function ends or I run out of gas. And then the EVM will be able to kick me out if I run out of gas. Okay. Okay, so some terminology. So there's gas, and then there's the amount you're paying for each unit of gas. It's just like a gas station. So the gas price is the market value for a unit of gas that you're willing to pay. So that is the gas price. And you can click on this gas station just to see, and it's market driven. And so you can see how much a unit of gas is going for in real time, and your wallet will do this. Like when you submit a transaction, it'll try and figure out what is the gas price that will actually get your transaction committed. And then it will ask you, is this okay? And then you'll hit confirm and it'll spend your money. There's also a gas limit, or in this case they call it a start gas. I want to start the execution with a certain amount of gas. So that the start gas is basically this thing. I want to start off the computation with a certain amount, is start gas. And what if the start gas is less than needed? You get this thing called an out of gas exception. So when you get this, this could be one of two things. You need to crank up the gas that you're sending, or there is something in your call that will cause the thing to crash or to exit. So the error, I think it's actually, the error, it might be smarter now, but it used to be out of gas was every error that you got back was out of gas, even if it wasn't out of gas, if it was like the sender didn't match the owner, like that would give you an out of gas exception, but I think it might be the case that you can get reasonable error messages back from Ethereum now. The transaction fee is then the gas price, the amount you're willing to pay per unit of gas times the amount of gas that you consumed. And this is the thing that gets debited out of your wallet when you submit a transaction to a smart contract. Okay, there's a system note. There's this block gas limit, which is similar to the block size limit on Bitcoin. The total gas spent by all of the transactions in a block has to be less than this limit. This is to cap the amount of computation that every full node has to do. So you don't want to actually bring the whole network down, and this global value allows you to make sure all the transactions are below. So, yeah.
Is that what determines the size of a block?
The number of transactions in a block, yeah, in terms of the computation. This is a stat. I don't know how often this changes, but like this is a. You can have a whole bunch of transactions trying to compete for the next block, and then their gas consumption has to be below that. Yeah. It's rare that you'll hit this, but this is just a system note. Okay, so because you're paying per instruction, like how much does a push operation cost? Well, it's gonna be minuscule amounts of currency. So the Ethereum currency denominations go all the way down to 10 to the negative 18th. So one way, 10 to the 18th way, this is the smallest unit of currency. 10 to the 18th is 1 ether. So you'll see here kiloway, megaway, gigaway, azabo, finny, ether, and then, yeah, nobody gets up here, but those are the currencies that are there. And the reason why you need it is because you're trying to do this highly granular charging operation underneath on the execution of your code. And then this is this is then the UI of Ether Converter Online. You will need to be able to navigate between these things in order to send an appropriate amount of currency to contracts. Okay. So yeah, these the ones in here are named after the people. So we talked about these systems. Well, we didn't talk about B-Money, but BitGold and ARPAO. That's why these things are named the way they are. Okay, so transactions, these are requests that are sent to modify state on the blockchain. They're signed by the originating wallet or the originating smart contract if it's sent by a smart contract. And there can be three kinds of transactions on Ethereum. You can send value directly from one account to another, that chain that I pointed to earlier. You can also create a smart contract on the blockchain. And typically you would instantiate this, you would send the code, sign it with your wallet address, and then it would create a new address that has the smart contracts account associated with it. And then you can execute the smart contract code. The transactions can include, as you would see from similar to Bitcoin, a from address, a to address, the gas price that you're willing to pay per operation, the gas limit for this transaction. So you have a gas limit for the transaction that you're sending, and then that block gas limit that's a global one. This is the transaction gas limit. The amount you want to send to the contract. So for example, if I want to deploy a contract that has 1 Ether associated with it at startup, so say it's like I create a vulnerable contract with 1 Ether on it and I want someone to hack it to get that Ether out of it, then what I would do is when I create the contract, I would attach some Ether to the contract creation step that comes out of my wallet when it gets created. So this is like fronting some money for the contract. And then the data is typically the function that you wanted to invoke is part of the data. And then your signature, your wallet signature to say, yeah, this is who is actually sending this transaction. Works very similarly to Bitcoin. Some implementation details. The blocks, so we talked about Merkle trees as being one of the ways that Bitcoin organizes its blocks to make the validation of transactions efficient. Ethereum uses something that's a derivative of this called Merkle-Patricia trees. And they're basically 3-branch tree versions of the Merkle 2-branch tree. So there's nothing that exciting about that. Bitcoin uses the SHA-256 algorithm, whereas Ethereum uses this Keccak-256, which is SHA-3 for hashes. So all of these hashes are being generated for consistency of a block. They're being, the chain is being done with SHA-3, the SHA-3 hash function. And then the proof of work is also going to use Keccak instead of SHA-256. So for this, once you've generated a block, then the miners are going to mine this block by taking the Keccak hash of this block and making sure that it's less than some difficulty. All right, so this all looks similar to what Bitcoin did. Another main, I guess this is really the main difference. So Ethereum really has to make this thing fast. You have to be able to put through a lot more transactions than Bitcoin is doing. And so rather than moving from a longest chain protocol, they initially implemented this thing called Ghost, which is I don't have the algorithm there. We'll talk about this later. The miners are rewarded if they do work on side chains that are eventually discarded. And these things are called, this is the greediest, heaviest subtree is the protocol acronym. And this allows you to mine sort of stale chains for a little while. Because what's happening is you want eventual consistency, and you want miners to be continually working towards eventual consistency. And this is one way to keep the miners going in the same direction, but increasing your throughput so that you can mine multiple things. You can mine some inconsistent things, but you can do it more quickly. So it's optimizing for transaction throughput versus transaction consistency per se that Bitcoin was doing. There's also a different mining algorithm, a programmable mining algorithm. So one of the things about making the, so I said that this is Kekak block. This is actually configurable. Let's see here. So they wanted to limit the ASIC and the GPU impact on the blockchain. So Bitcoin is definitely focused to have centralized mining because of the hash algorithm. One of the ideas of Ethereum, and one of the things that they're moving towards, is to get rid of that. To make the thing so that the ASICs, you can't build this into hardware as easily. So that's what their mining algorithm attempts to do. And then you have a difficulty that's adjusted at a much finer granularity than Bitcoin's every 2 weeks. Okay, so the blocks go much faster than Bitcoin. So the block time is about 12 seconds. The amount of currency that a block will generate is variable. So the money supply is not restricted in Ethereum. So it's inflationary. Right now it's around 5 ETH to mine a block. And if you mine a block that's ultimately not going to be used, you get 1/32 of an ETH. So you get some money back. And then eventually you'll want to mine the one that everyone else is mining. And then the block size is miner controlled. And I think that's done with the limit. Okay, so full nodes. So if you want to run, yes?
What's the point of encouraging miners to mine those side chains on the blocks?
So rather than always waiting for that next state, you can actually more aggressively. So as soon as Bitcoin has a block, everyone abandons their work and then moves on to something else. But if you allow multiple miners with different collections of transactions to do the mining, then you can actually make a little bit more parallel progress. That's the nominal notion, yeah.
What if your transaction is on the side chain that's then not chosen? Then is that not invalid?
Then you would want to wait for the again, similar, you would want to wait for the confirmations on, but you're getting more like the depth is increasing much faster. You don't have to wait 10 minutes. So it's a little bit faster and looser with the consistency. It's trying to, it's trying to be aggressive in accepting new state, and then it's using this algorithm to prune it off eventually. Yeah. But an Ethereum node, because it's doing all of this stuff, requires a lot of hardware. So the actual full node is about 1 terabyte. Oh, that was last year. I don't know what it is now, probably 2 terabytes by now. Actually, I have a graph. And it requires a sizable machine and network connection to run. This is why you're going to be running your nodes on Google Cloud rather than a Linux lab machine, which Kat would get really mad at me for if I had you all bring up Geth on one of their nodes. So the size of the node is unpredictable, right? So, and you'll see if you actually try and run a full node, you'll bring it up, and about 3 days later, you'll have the full node, like synced. Like if you actually, in the command, you'll see the flags. I'm going to have you run a light node, which is something different. But if you actually, on your Google Cloud instance, bring up a full node and set it to full node sort of functionality, yes, you can build and transact and do all your stuff on that full node. But yeah, it would take you 3 weeks, and you would have to leave that thing up the entire time to get all the updates to participate in the transaction. So you would have to pay for that cost. So you can see there are different curves. So this is the Bitcoin curve. This is what Bitcoin wanted, was linear, but based on the Geth, what algorithm Geth is using to increase the transactions, you get some kind of curve like this, which would make your node unpredictable in terms of rate. Okay, so as it turns out, many of these full nodes are run by companies such as Infura, which just got acquired by someone. I forgot who it got acquired by. Due to the resource constraints and the management costs, these are being run by industry folks. They're the ones who have the money to produce this. This was the opposite of what Bitcoin wanted. Bitcoin wanted anybody to run a node. Here, you do need some resources to run this thing. There are very few archival nodes. Archival nodes have the state of the entire blockchain, and this is a number that is the maximum limit. This is a 16,000 total archival and fast nodes. A huge percentage of this are actually fast nodes. So the the Ethereum network is much smaller. The number of full nodes on the Ethereum network is actually much smaller. Okay, so what we'll be doing is running a light node. It is a light client that connects to full nodes. So it contains all the block headers, and it's about 100 megabytes to run. So when you bring up your light node later on in this class, it'll take you maybe like an hour to get everything up and running. It can't execute write transactions as full nodes do, but all the read operations, like if you want to get a contract balance, you could do that on your light node immediately. If you want to see the balance of your wallet or any of your wallet statistics, then a light node has everything that it needs to answer those questions directly. It's when you actually want to transact and change the state of a contract that you need a full node to do so. And you'll see with MetaMask, MetaMask by default will point to the Infura full nodes to actually do the transactions when you're trying to write into the blockchain. Okay. So you have these full nodes running, and then your light client is going to connect up with the full node whenever it needs to submit a transaction that's a write transaction, but then it can process all of the reading on its own without actually having to communicate with the central network. And then every once in a while, a summary of the Merkle-Patricia routes are given from the full node to the light client. Okay, and this was implemented last year to try and scale up Ethereum. Yeah.
Is there any load balancing for light clients to connect to full nodes, or could you just have to pick one that you hope has capacity?
You pick one that you hope has capacity. Right now, you pick one. On the back end, I don't know. So you have a name, like Infura.com. On their back end, they might do load balancing transparently. I don't know. But you typically hard code it either in your Web3 app. So if you have a web app that talks to Ethereum, then it's using this thing called Web3. It's a JavaScript package, and then it is hard coded, or you can hard code which full node that thing talks to, and so that full node could actually be a load balanced thing, but you would typically write that in as part of your app. Okay, so there are a lot of scalability issues with Ethereum. This is why the only thing on Ethereum right now are a lot of toy applications. The thing that they're trying to do this month is Istanbul. This was deployed to Ropsten, and I sent this article out. This was sent to Ropsten as a test, and I couldn't do any work that weekend on Ropsten. So I don't think it went well. I haven't read the postmortem on this, but it had some mixed results. And one of the things with Istanbul is that they're trying to move away from ASIC-based hashing as a mining operation. So this is actually good, right? Because that kind of resource consumption is ridiculous to what is the benefit that these blockchains are giving us that would require us to consume that amount of energy? Well, it's not. So they're looking at this initial step towards a proof-of-stake model was this progressive proof of work to get rid of the ASIC farms that are dominating the blockchain. So that didn't go so well, unfortunately. Eventually, this is going to be a stepping stone to Ethereum 2.0. And this actually was just in the news last week because I think their DevCon was in Japan last week. They are talking about moving to a full proof-of-stake model in Ethereum 2.0, and this would be a hard fork of the blockchain. So you would start anew with a different mechanism. So what they wanted to do is put security in the hands of those with the most to lose if the security is broken. This is where you're aligning incentives in a system. This is more of a social and a human nature thing. You want to make sure the people with the most to lose are given the responsibility for securing the blockchain. So the miners don't necessarily, the miners, as it is right now, the miners do have some incentive to make sure that the mining is done properly. Because if people lose faith in the mining being fair, then all of the Bitcoin that miner currently has from mining all of those blocks will get devalued. So there is a certain alignment that is happening with Bitcoin that you also want to have happen with Ethereum, but just without the massive resource consumption. So this is what proof of stake is. So Casper proof of stake is the idea. You have the notion with based on the amount of ether you're willing to stake to a block being valid, you'll be selected to validate the next block. So you're putting money up every single time and say, hey, trust me, I put some collateral up, choose me to validate the next block. And then if you validate the next block and everybody agrees it's a good thing, then you would get your stake back plus a little bit extra. So we talked about all of those incentive systems earlier. The other big thing was this support for sharding. So side chains that you would aggregate the transactions for, create a hash, and then commit the hash is a hierarchical way of managing state rather than having everything go to the main Ethereum chain. So this is one of the other big features of Ethereum 2.0. And then if you have those things, then you may be able to scale the thing up where a lot of people can use the blockchain. Okay, so here's a look at distributed apps on Ethereum. This is the number of new apps per month. And you can see there's this huge uptick in 2017 and 18. It's sort of this is the crypto winter. It's sort of fallen off. And so hopefully for this class, hopefully we'll get a little bit of a spike because you'll be deploying a lot of contracts in this class. But this is this is a number of new ones. So yeah, we won't put a dent into that. Okay, so that's all I have for Ethereum. Next class, we're going to